till now we have seen about the translational mechanical systems. Now we will see about the mechanical rotational systems. So mechanical rotational systems. So let us go step by step in the translational and then mechanical rotational systems. So in the mechanical rotational systems, the moment is in the form of a twisting moment, angular moment. The force is in the form of a twisting moment. That twisting moment of force is called the torque, and the angular moment is it is in the form of a rotations that they will be doing. So whatever we have seen in the translational mechanical systems, more or less the same thing we'll see in the mechanical rotational systems also. So the first thing that we are trying to see in the mechanical rotational systems is this. Suppose there is any body of mass and it is having a moment of inertia j. So this is some sort of a ideal mass, and it is having, assuming that it is having negligible friction elasticity. So now you are trying to apply some sort of twisting moment of force that you are doing here. So that twisting moment of force is called the torque. You are applying certain amount of torque. So the twisting moment of force is the torque. So when the force is twisted, so the moment that will come here is in the angular moment. That angular moment I am calling here it as theta. So here if you observe carefully, so whatever the T is the applied force and Tj is the opposing force for it. So the total, the opposing force is equal to the applied force, that is directly proportional to the angular momentum here, that is d square theta by dt square. So that we can write as T is equal to, so this that is Tj is equal to k into d square theta by dt square. Okay, so this is how it is written for the torque balance equation for the ideal element. Suppose if this element is ideal rotational dashpot, so with one end is at fixed reference. Suppose this is our dashpot, this dashpot is fixed at one end. Okay, so this dashpot is fixed with one end reference, and assuming this is having some constant, and here you are applying some sort of a torque and it is moving with a certain angular speed theta, then the applied torque that is supposed to oppose that force, that I am writing as Tb. The Tb is directly proportional to d theta by dt. So taking that into consideration, Tb is equal to the applied torque T, that T is equal to Tb, the torque that opposing due to its friction, that is equal to B into d theta by dt. This also you can write. Suppose if it is moving at the both ends, then at the time suppose instead of that here if the dashpot is having without any reference, and you are applying say the torque T1, and it is angular moment that is having theta 1, which is having the coefficient B, and it is having with the theta 2, then T is equal to Tb is equal to, directly I am writing B into d by dt of theta 1 minus theta 2. That simple it is. So now similarly let us consider the ideal spring with the one end is fixed here. So this ideal spring here I am taking here, this is the ideal spring. This ideal spring is fixed at one end and it is having constant k, and the torque is T and the angle is theta, then we can write as the whatever the applied torque that we are giving, it is opposed due to the torque elasticity constant Tk. So T is equal to Tk, that is Tk is directly proportional to theta. So if I remove the constant, Tk is equal to T is equal to K into theta. Suppose if the ideal spring with angular displacement at the both ends, without having any reference at the both ends, then it is say, assuming this is the angular spring, ideal spring. So here you are applying a torque T and it is a moment theta, say 1, and the spring constant is K, and there is another angular moment of theta 2, then the total Tk is directly proportional to theta 1 minus theta 2. So if I remove Tk is equal to Tkk, the total torque T is equal to Tk is equal to, I am removing the proportionality constant, so here I will get theta 1 minus theta 2. That is how we can get simply all the mechanical rotational systems. So based on these mechanical rotational systems, we can try to draw we can solve some sort of a problems easily, and then we can able to, whatever we have did in the same mass system, same thing we are also going to do here. So the things are like this here. So let me take one example of the thing. Suppose, so let us draw a differential equations for the rotational mechanical system, and to obtain the transfer function for it. A transfer function means Laplace of output by Laplace of input. Suppose the torque is the input, so whatever the angular momentum that is happening, that is the output. Say for example, so a system is there, the system is having the mass with its inertia, that I am writing inertia as J1, that it is connected to the torsional spring to another mass which is having inertia J2, and it is connected to the dashport and connected to a reference. So here you are trying to apply the torque. So when you apply the torque, it tries to make a moment. It is having a fixed constant K, and here the moment, here the theta that we wanted to find, it is having constant B. Now for this particular system, we wanted to find out the transfer function. As I already know, the transfer function is the Laplace of output by Laplace of input. Here the output is theta, so if I write in terms of Laplace domain, it is theta of s by t of s. We need to find out this. So now let us write down the step-by-step equations how to solve this particular. So whatever we have written, in the mass free body diagram of the mass, similarly here also we'll write the same sort of diagram, okay, and then we'll try to solve it. So I'm just breaking into two parts so that I can able to solve in this particular thing. So here, firstly, the total torque that is equal to total torque that is applied. So the torque that is experienced to J1 plus the torque that is given to the spring constant, because the constant is inliced between J1 and J2, that is equal to total applied torque. So that I am writing as J1 d square theta 1 by dt square plus K into theta 1 minus theta is equal to T. Now if apply the Laplace transform to this particular system, what I can write is J1 s square theta 1 of s plus K theta 1 of s minus K theta of s is equal to T of s. So taking theta 1 into common, I can write as J1 s square plus K into theta 1 of s minus K into theta of s is equal to T of s. This is for the the angular displacement of mass with a moment of inertia J1 and T1. It is basically the free body diagram of J1. Similarly, the free body diagram for the J2 also we should write. Okay, what are the forces that are acting on the J2? That is the torque T J2 plus the torque due to this frictional coefficient B, and then the torque due to the spring coefficient. So there is no another element, so that is equal to 0. So this one I am writing as J2 d square theta 2 by dt square plus B d theta by dt plus k into theta minus theta 1 is equal to 0. So applying the Laplace transform here, J2 s square theta 2 of s plus B s into theta of s plus k into theta of s minus k into theta 1 of s is equal to 0. So from here, theta 1 of s is equal to J2 s square plus bs plus k divided by k into theta of s. So taking those two into consideration, here theta 1 is there, here theta is there. Taking both of them into consideration, okay, here what I can write, J1 s square plus k into theta 1. Theta 1 is how much? Whatever it is, right? J2 s square plus bs plus k divided by k into theta of s minus k into theta of s is equal to t of s. So by substituting these values and then rearranging here, theta of s by t of s can be written as, because this will be multiplied here, this will be multiplied here, theta take common, theta of s by t of s. If you will write, it will become k divided by J1 s square plus k into J2 s square plus bs plus k minus k square. So this is the complete transfer function for entire system. So that is how you can draw the transfer function. I mean, you can write the transfer function for the entire system like this. So in the similar fashion, let us solve for one more critical thing, and then we'll try to go for another particular system. So let us draw one more particular system, that is, the system is something like this. So now we are trying to draw the differential equations for the mechanical rotational system as shown in this particular figure, that is. So let us take another scale, white color. Yeah, so let me assume there is a moment of inertia having the mass here, and there is the frictional coefficient, there is a dashport, and there is another mass and another dashport. So assuming this is compared to reference, so assuming these are all, I am just comparing with the reference, these are all taking as the reference. So here I am giving certain amount of torque T, it is moving with an angular theta 1. So this constant I am considering as a K, this constant I am considering as B12, and this is I am considering as theta, this is I am considering as B. So finally what I want to do is I wanted to draw what is theta of s divided by T of s. So Laplace of output by Laplace of input is what I wanted to find out. So it is very simple as per the last whatever we have seen. Similarly, we will also draw the free mass, free body diagram for the moment of inertia, and then we'll try to solve it, and then the similar fashion that we can do whatever we have done earlier. So let me change the pen settings for it. So I'll just take yellow color so that it looks good. So let us first of all draw the free body diagram for the J1. So as we are drawing again, again and again, the same thing we are drawing here also, the free body diagram for the J1. That is T J1 plus TB12 plus TK is equal to the total T. That is that much simple it is. So whatever it is, the question is given, you have to think logically and write very carefully. That is J1 d square theta 1 by dt square plus b12 d by dt of theta 1 minus theta plus, because this is sandwich between this k and b12 are in between the j1 and j2, that's why I'm writing k into theta 1 minus theta is equal to t. So taking that j1 s square theta 1 of s plus b12, taking that theta 1 of s minus theta of s plus k into theta 1 of s minus theta of s is equal to t of s. From it, if you take theta 1 as common, theta 1 of s, if you take common, j1 s square plus s into b12 plus k minus theta of s, if you take common, b12 into s plus k is equal to t of s. So if you similarly if you do the free body diagram for the J2, okay, if you draw the free body diagram for the J2, how it is looking, let us see it here. So here, so first of all, what are the things that are acting on J2? So its own force Tj2 plus Tb12 plus Tb plus Tk is equal to 0. So Tj2, j into d square theta by dt square plus b12 into d by dt of theta minus theta 1 plus b into d theta by dt plus k into theta minus theta 1 is equal to 0. So then again applying the Laplace transform. So it is J2, right? Yeah. J2 s square theta of s minus b12 s into theta 1 of s plus s into theta of s into b12, so we are taking those into consideration, b12 plus b plus k into theta of s minus k into theta 1 of s is equal to 0. So taking that theta into consideration, so theta of s, theta of s if you take into common, theta of s if you take common, s square j2 plus s into b12 plus b plus k minus theta 1 of s into b12 plus k is equal to 0. Now taking this into consideration, theta 1, if you write, theta 1 of s is equal to s square j2 plus s into b12 plus b plus k divided by s into b12 plus k into theta of s. So now we have to substitute this theta 1 into here so that you will get all the things very easily. So whatever the theta 1 is there, let's substitute it here, and because it is in the form of theta of s, you will get theta 1 in terms of theta of s. So I'm just doing that now. Okay, so now I'm just substituting those values here. j1 s square plus s into b12 plus k into j2 s square plus s into b12 plus b plus k into theta of s divided by s b12 plus k minus s b12 plus k into theta of s is equal to t of s. So reshuffling that, theta of s by t of s is equal to s b12 plus k divided by j1 s square plus s into b12 plus k into j2 s square plus s into b12 plus b plus k minus s b12 plus k whole square. So that is how you can simply write all those equations in a very easy and lucid fashion. So it will be very easy to solve that kind of things. Yeah.